Hello, class. So in this video, we'll continue on section 2.4. In the previous video, we talked about this theorem. Given a first order linear differential equation with an initial condition, so an initial value problem, there's a way for us to find an interval for which we're guaranteed that a solution for this initial value problem exists and for which it is unique. So I mentioned that in the previous video. I'm not going to go over that again. So now let us go to the more general version of the theorem. So again, as I mentioned, this is going to be a little bit more general. We're going to not require linearity for our first order differential equation. So the way to determine the interval is actually going to be a little bit more complicated. Let's see what the theorem says. This is theorem 2. Let R be a rectangular region in the xy plane, defined by some interval AB on the x-axis and some interval CD on the y-axis. So some interval AB on the x-axis, some interval CD on the y-axis. And here, this is a picture I took from one differential equations book, by Dennis Sigil, I think. So as I'm reading this, you can look at this picture and kind of follow along. Okay? Suppose you have this rectangular region in the xy plane, and suppose it contains the point x0, y0 in its interior. Right, so some point. So here's the point x, y0 in the picture. So it's a little bit blurry, but this is the point, right? So it's precisely this point here. And the region in blue is, of course, the rectangular region R. Okay. So I have this region with this point inside of it. Oh, I guess I should have called this F. Okay, so let me write it as f of x, y. So if f of x, y, and here's why we need partial derivatives, and the partial of f with respect to y are continuous on this interval R, not in this interval, sorry, and this region. So this is where it's a little bit hard because we know how to check continuity when we have one input variable. How do we check continuity when we have two input variables? This is something you're going to learn in Calc 3. For us, it's going to be a little bit hard, but the general rule that you want to follow, and again, that's why I won't use this theorem too much because of this, but a lot of the functions that are continuous in the one-dimensional case are continuous in the two-variable case. So for example, any polynomial of two variables, so p of xy, so something like x cubed plus 3xy plus y squared, any polynomial is going to be continuous everywhere. The trig functions are going to be continuous. So for example, cosine of x plus y, right? This is going to be continuous. So the functions that are usually continuous are going to be continuous in the two-dimensional case. You just have to be careful about the same things. Like, are you taking square roots of things? Are you taking natural logs of things? Are you dividing by some expressions? The same rules apply. Right? But if you have simple things, like you're not dividing by anything, just multiplying things, just adding things, just working with functions that are already continuous, then whatever function or expression you have is also going to be continuous in the two-dimensional case. Now, I'm not going to say more than that. Something you're going to learn in Calc 3. Hopefully for now this works. Okay. So assuming that f of x, y, the partial derivative of f with respect to y are continuous on R, then there exists some interval around x0, right, which we're going to call this interval y sub naught or y sub 0. Now the interval y sub 0 is also labeled here in this picture. Right, so I naught or the I sub naught or I sub 0 is this interval around x0. So it's an interval containing x0, and that's contained in the original interval for x. Right? So the interval for x originally for this region R was the whole AB interval. So you're guaranteed that you can find some sub-interval or some interval inside that original interval AB, which contains x0, and you're guaranteed that a unique solution to this initial value problem exists on this interval. So as you can see, it's very similar to the previous theorem. Again, what are the distinctions? We have the initial value problem. We don't require this time that our differential equation is linear. So it's more general. But in terms of finding an interval for which a unique solution for this initial value problem exists is kind of similar. What do? You first find a region in the xy plane, so some interval about x and some interval about y, for which both the function, right, so that whatever expression we have on the other side of the y prime is continuous, and also the partial derivatives are continuous. Once you have that, you don't know what the subinterval I sub naught is. So this is why this is not as powerful, because this is not saying that a differential equation that's a solution to this initial value problem exists on AB. It's saying that it exists on some subinterval of AB. So in this case, we don't actually know precisely what this interval is for which the solution is defined. So again, when we lose linearity, we lose some things. But other than that, we at least know that some interval exists for which a solution exists. So again, if you know that, it's worthwhile trying to actually solve the differential equation and the initial value problem. So that's the idea. Again, it's a little bit harder because you need to deal with continuity in functions of two variables. And again, you're not guaranteed what the interval actually is, where the solution is defined, but it's still useful. Okay. Now, let's again, similar to before, work through an example. So, example 2, determine whether the initial value problem, dy dx equals x times y to the 1/2, or the square root of y, so it's an initial value problem, so we need an initial condition. In this case, y of 2 equals 1. Determine whether this initial value problem has a solution using theorem 2. Okay. So let's use theorem 2. What do you need to do? You want to rewrite your differential equation in this. Actually, let me get rid of these for now. You want to write your differential equation in this form. Y prime equals something. So basically solve for y prime first. In this example, we already have y prime by itself on one side of the differential equation. So we're good. Okay. So for our purposes then, whatever's on the right-hand side of the equal sign is our f of xy. So that's a little bit hard to see. So let me go here. So for our purposes, f of xy is whatever you get on the right-hand side after you solve for the derivative. So in this case is x times y to the 1/2. Okay. Now, what else do we need? So we wrote it in the right form. We have our f of xy. Well, we also need the partial derivative of f with respect to y. So let's find that partial derivative. Okay. So partial of f with respect to y. How do you find this? Remember, it's as if you were taking the regular derivative of this function with respect to y, treating any other variable as a constant. So for our purposes, in taking this derivative, x is a constant and y is the variable. So as before, you can worry about x until later. So yes, x is there. So all you need to do is find the derivative of y to the 1/2 with respect to y. I'll use the power rule, right? Bring 1/2 down, subtract 1 from the exponent. So bring 1/2 down, subtract y from the exponent, multiply x back in. So this is the partial derivative of x with respect to y. Of f with respect to y, sorry, not x. Okay, so recapping. We wrote our differential equation in the right form, right? We solved for y prime by itself. Right? Whatever's on the other side is f of xy. And we also have to find the partial derivative of f with respect to y. Now what do we need? Now we need to find, so going back here, we're looking for some region R, so some interval about x. So let me underline it again. We're looking for some interval around x, and some interval around y, for which our functions that we found, f of xy, and the partial of f with respect to y are continuous. Okay. So these are our f and our partial of f with respect to y. We want to find some interval around x for which interval around x, and we want it to contain the initial input. So some region R you see in the picture, we want the region R to contain the initial input. So we want some interval around x, which contains the x coordinate of the inputs, in this case 2. And we also need to find some interval around y, so an interval with respect to variable y, that contains the output of our initial condition. So again, if you look here, the initial condition is given by y of x naught equals y naught, and we want the region R to contain that point, x naught, y naught. So for us, we want an interval about x and an interval about y that contains, for the x coordinate, that contains the input 2, for the y coordinate that contains the output 1. Okay. So now, again, it's going to be a little bit hard to explain how continuity works in more than one dimension, but as I mentioned, everything is continuous that should be, and you only have to worry about the usual things for the most part. For example, here, x is fine, right? There's nothing working with f of x, y first. So actually, let's do it like this. Let's separate it into parts. So intervals for f of x, y. So let's look at the x coordinate. There's nothing wrong with x. X here can be anything, right? There's no square roots, there's no dividing by x or anything like that. So for x, we can use the interval. Well, we can use the interval negative infinity to infinity. There's no restrictions on x. Now, we need our functions to be continuous on these intervals, right? So we need continuity here on whatever intervals we find. Now, since I mentioned that continuity works basically the same, for x here, this is fine. Right? This interval is exactly fine. Right? There's nothing that prevents continuity for the x portion of this function. You have to be careful with y, though. Because for y, we have a square root. As you know, for square roots, you need the input to be greater than or equal to 0. So we're actually fine, just as you would expect in one dimension. Well, it's the same thing here. As long as you take the variable y to be greater than or equal to 0, not only is the function defined, but it's continuous there. So we say f of x, y is continuous here. Now let's look at the intervals for the partial derivative of f with respect to y. Now let's look at this function here. And again, we're going to start with x. Again, we have x by itself. There's no restriction on x here. We're not taking square roots, we're not dividing, we're not inside a natural log. So in particular, there's no restriction on x. We can write again the interval negative infinity to infinity. This region is going to work for, in terms of the x variable, for continuity. Again, as you would expect, this function is going to be continuous for this part of the x interval. Now, since a function of two variables, this is a region in the xy plane, so we also have to find the y portion of this interval. So for y, again, we have to be careful. Not only do we have a square root, but we have a negative exponent. So if it's easier to see what's going on, you can write it as x divided by 2 times the square root of y. So remember, you can make the exponent positive by moving it to the bottom of the fraction, and vice versa. So what's going on here? Not only are we taking the square root of y, but we're dividing by that. Okay? So the square root of y restricts our domain, right? Y has to be greater than or equal to 0. And you can only put non-negative non-negative inputs in the square root. But we can't actually include 0 because if we make y equals 0, 2 times the square root of 0 is 0. It would be dividing by 0. So the fact that square root of y is in the denominator is also saying that we can't include 0 in our domain. So for y here, instead of using the interval negative 0, 0 to infinity, including 0, we're going to use 0 to infinity. And as again, I can't prove it for you, but as you would expect, this function is continuous here, as I told you to think about it. If it is continuous in the one-dimensional case, it's continuous in the two-dimensional case for the most part. Now, again, geometrically, you want to think of each of these things. So you want to think of, let me use a different color. You want to think of this here and this here as squares in the xy plane. The x-coordinate is telling you, so this is the xy plane. The x-coordinate is telling you where to go in terms of the x-axis. So say if we were going from x equals 0 to x equals 2, let's say this is 2, and we're going from y equals 0 to y equals 3, if those were our intervals, then we would be looking at this square here. So again, even though I'm writing them as intervals, think of these intervals as being the sides of a square. Okay. Now, we found the intervals for which our function and our partial derivative with respect to y are continuous. Once we have that, okay, we need to make sure that the input x equals 2 and the output y equals 1 are in these intervals, okay? I think they are. X is in the interval negative infinity to infinity. Y is in the interval 0 to infinity, or 0 included to infinity. So that works. Finally, both functions have to be continuous on these intervals, right? Just like we did in the previous theorem. We're working with two functions. We took the interval on which both functions were continuous. Same here. We need to take an interval on which both functions are continuous. In this case, so for x, well, both functions are continuous on negative infinity to infinity. Oops, not including. Now for y, well, one function is continuous on 0 to infinity, not including 0. The other one is continuous on 0 to infinity, including 0. Well, it has to be continuous on both, so that means that we have to take the smaller interval. We have to take 0 to infinity without including 0. Because if we were to take this one, our function partial f partial y, or the partial derivative of f with respect to y, wouldn't be continuous. Right? So we have to take the smallest of them. So both functions are continuous now that we've found our intervals about x and about y. What do we need? Well, let's see what the theorem says. So once we found this region R, in the plane, which we found, so for us, our square is like an infinite square because both of the sides are infinitely long. You don't have to take, I always say to take the largest interval, right? So you can take something smaller, but let's just take the largest one. So we found our interval that contains the point x naught, y naught. We found that our functions, both f and partial f with respect to y, are continuous there. So what are we guaranteed? Well, that there is some function, right? So what can we conclude? In conclusion, by theorem 2, there exists some open interval I naught contained in the interval we found for x, right? So this is an input interval, if you see here. The interval I naught is contained in the interval we found for a and b. So for the interval we found for continuity, I naught is just some subinterval. We don't know what it is, right? So this is why this theorem is not as powerful as the other one. But we know that there exists some open interval I naught contained in the interval for continuity we found for the x variable, so contained in negative infinity to infinity, for which this initial value problem has a unique solution. And again, if you're doing the homework, I would like you to write a conclusion like this. So conclude your work. So if you see in terms of the work, it was basically very similar to what we did in the previous theorem. Get the differential equation in the right form, right? Get y prime by itself, find label f, right? Find the partial f with respect to y, find intervals with respect to x and with respect to y, on which both functions are continuous. Once you've done that, you're basically done. You're guaranteed, we don't know what that interval is, but you're guaranteed that there exists some sub-interval of the interval you found for the x-axis for continuity, for which a unique solution for the initial value problem exists. In terms of the picture, the graph here, so what you see as light blue or darker blue, that's the function that they found or that they graphed that represents, okay, there is some solution to this initial value problem on this sub-interval I naught. Okay, so I'm talking about this function here. That's basically it. So again, these things are more theoretical, but if you follow these examples, again, just follow the steps that I did here, you should be able to work with them. And again, I spent a little bit of time explaining why existence and uniqueness are important. Hopefully that convinced you, and now you know how to, at least for these, I guess more generally, given a first order ODE, not necessarily linear, you can find, at least you can guarantee some interval. You don't know what it is, but you can guarantee some interval for where a unique solution exists. And in the case of a linear ODE, you can actually find the actual interval where you're guaranteed that a solution exists for the initial value problem.